So now that we've seen what NCR does, we've seen what factorials are, now we can actually finally do the binomial theorem. So this is going to help us in order to solve more complicated binomials. So let's take a look at it. This is again for expanding a binomial like a plus b to the power of n. By the way, I love this one. This is perfect for here. Look, expand. You just made it bigger. So this is how we do it, okay? I just want to show you again how it would go if we were going to do the Pascal's triangle method. I just want to compare that, okay? So if I try to do like, let's just say I tried to do a plus b to the power of 3, let's just pretend. If I was going to do Pascal's triangle method, remember I would first go write out Pascal's triangle, 1, 1, 1, 1, 2, 1. Then I go 1, 1 plus 2 is 3, 2 plus 1 is 3, this is 1. I would then write these all out, wouldn't I? I would say this is 1, then I would write it like this, plus 3. I just want to show you a contrast to this right here, because this is going to be really important. This method I'm about to show you is going to be much faster. I just want to show you it's actually the same thing. So if you know about Pascal's triangle method, I've got another video that I did about it. But here we go, it goes like this. So 1, then a, b, then 3, then 3, then 1. So in other words, these are your coefficients, right? These numbers right here. This is your coefficient, 1, 3, 3, 1. That's why we found Pascal's triangle. And then remember what we learned. I'm not done yet, sorry. I have to also do the powers. The powers have to go down, so 3, 2, 1, 0. And these ones over here, they go up. They go 0, 1, 2, 3. Now, this formula right here, you get on your formula booklet. So you don't have to memorize it. I just want to show you that this is actually telling you what I've just done. Watch it very carefully. First of all, let's look at this. The very first term, if I actually did it, let's say I actually wrote it all out. 1 times a cubed times b to the 0. Well, b to the 0, isn't that just 1? Anything to the 0. So do you notice? And it's just 1 times a cubed. See, it's just a cubed. This one here, this next one, what is this? This is 3a squared times b. The next one then is, do you see it's 3 and it's ab squared. The next one is, well, this one right here cancels out and I just get b cubed. I just want to show you if I actually fully expanded it, this is what I would get. Now look carefully at what this formula actually tells you. It says, hey, your very first term is just a to the power of n. Well, in this case, a was just a, n was 3. Do you notice? Look, a to the power of n. The next one, they say it's NC1. Turns out that's how you get that number 3. So this right here is NC1. Then you notice then the next one is going to be NC2, then NC3, and so on. So these NC things, they just keep going up. That's to tell you your coefficients. Notice what happens. It says, look, your powers of a starts off as n. The next one goes down by 1. Well, yeah, look, 3, 2, 1, 0. Look, it goes down by 1. It keeps going down by 1 until there's none left. Conversely, look at what happens with the b's. There's no b here. That's because it was b to the 0. The next one has 1b. Do you see there's only b to the power of 1? Keeps going up until you're up to b to the n, which is the last term. So if you look carefully at this final form, it looks like this. The trick is, and this is what I'm going to tell you this, that if you're HL, you need to be able to use this formula quickly. It takes practice. If you're SL, what I recommend is this, use a hybrid. So there's a much faster way of doing this, and I like Pascal's triangle method. You know, this way of just writing a's and b's and doing your exponents going down, your exponents going up. Except I don't like finding Pascal's triangle if the exponent is too high. It's really long to do. So what I like about this method here is it allows you to kind of cheat. See what these things are right here. Let me just write it down, a quicker way of doing it. So let's just say if I was going to do this thing, this a plus b cubed, what I would actually do is I would write it like this. Watch very carefully. I do NR. I'm going to write it with this notation, you know, for these coefficients. Watch very carefully. What I'm going to do, I'm going to say, all right, well, there's how many terms? There's going to be 4 terms. So I'm going to write it like this. I always do a space, you know, and then I go like this. 1, 2, 3, and 4 terms. So I'm writing out actually the 4th term here. So like this. This is 1, 2, 3, 4 terms. The very first one, watch carefully now. I'm going to do this. You got it in purple. This is NR. So this is, if it's to the power of 3, it's going to be 3, 0. Next one's going to be 3, 1. Next one's going to be 3, 2. Next one's going to be 3, 3. This is this NCR notation. This is like 3, C, 0, like this. just so you can see how I'm doing it. Then these next terms, of course, those are still the a's and the b's. See, I like the Pascal's triangle sort of method of doing it, this algorithm. This one right here I think is nice. Then it goes, 3, 2, 1, 0, 0, 1, 2, and 3. So do you see, this way, this hybrid, is we use the Pascal's triangle method, except we don't actually need the triangle. Do you see how powerful this is? Because if I have to the power of 18 or something like that, just think, all right, well, it's going to be 18, 0, 18, 1, 18, 2, 18, 3, 18, 4, 18, 5. So you can sort of figure it out a lot quicker what you need. Then you focus on the one you need. Let's pretend you just needed this one. All right, fine. Then you go ahead and calculate 3, 1. In other words, what's 3C1? And you'd use your formula here to get it, right? So let me show you a real example here. This is one from an IB question, actually. So find the constant term in the expansion of x squared plus 1 over x to the 6. I didn't make it too hard. It's medium difficulty, right? Because it's to the power of 6. It's not that crazy. But I don't want to do it using Pascal's triangle method. I'm going to do it using this hybrid. So first I'm going to write out all of my different terms. So I know I'm going to have 7 terms. If I want to do this whole thing, I'm going to have 7 terms. There's always a coefficient, an a, and a b. Right, so I'm just leaving space for it. So although it seems annoying, which it is, I'm just going to show you quickly how to set it. So 1, 2, 3, 4, 5, 6, 7. All right, so what is this first one? It's going to be n, so which is 6 here, 6, 0. This is the important part. This is 6, 1. This is 6, 2. So basically, if I need any of these coefficients, here's how I'm magically going to get any coefficient I need. Wait a second. I can't seem to count. I see my mistake. I did 2 twice. There you go. 6, 4, 6, 5, 6, 6. Well, then I do my x squared and my 1 over x everywhere. So do you see this is slightly long? And when you get more practice, you're going to see you don't even have to write them all out, but it's not a bad idea just to write them out until you find the one you need. Okay, so x squared, 1 over x. This is slightly long, but it's not that difficult. And now I know what my powers are going to do. My powers are going to go down for these ones here. So it's going to go 6, 5, 4, whoops, can't seem to count here, 4, 3, 2, 1, 0. And my exponents are going to go the opposite for the b here. So 0, 1, 2, 3, 4, 5, and 6. So now that I've done this, we don't have to do all of them. Try to find out which one will be a constant term. And remember what constant term even means. It means the power of x is actually to the 0. In other words, there's no power of x here. So somehow they cancel out. Well, look carefully at this one right here, the powers of x's. Let's just look at powers of x. Let's just look at this one here. So this one here would be x squared to the 6. That would be x to the 12. All that would be divided by x to the 0. That doesn't work. That won't cancel out. I'm going to have power of x to the 12. So that doesn't work. So it's for sure not that one. Do you see how I can sort of determine it's not that one? And so on. I can keep going like that until, look very, very carefully. One of these will actually cancel out the x's. Do you notice I'm dividing by x's, so I have to be careful. Look, this one is going to be x to the 2 times 4, which is 8, divided by 1 over x squared. So that means this right here, they won't cancel out. Do you see which one does cancel out? There's one of them that does. Look right here. Look at this one. Look very carefully here what's going to happen. X squared squared is going to give you x to the 4th over x to the 4th. Hey, they're going to cancel out. That's why I can just focus now like a laser on just this one. I ignore the rest of it. They're dead to me. And I just look at, all right, I need 6, 4. I have x squared squared. Let's just make sure it works, right? It's x squared squared times 1 over x to the 4th. Well, what does that give me? I have this 6, 4, whatever that is. We'll determine it in a second. X to the 2 to the 2 gives me x to the 4th. Divide that by 1 to the 4th, which is just 1. Times 1 to the 4th over x to the 4th. And look at that. Thank goodness they do really cancel out. So I just need to know what is 6C4. Now I could do this without a calculator if I wanted to, right? I could use that formula, or I could just use a calculator. It depends on if I'm allowed one or not. Let's say I am allowed a calculator, then I'll just do it like this. I go to menu, I go to probability, I go to combinations, and I say 6, 4. This way I didn't have to do Pascal's triangle. So now then the answer is just 15, and I'm done. Wasn't that actually quite easy? So this is sort of how we can look at these kind of questions here. Okay, I just want to make sure you feel sort of semi-comfortable with these. It does take some practice, but this here is how we can do this. Okay, the constant term, you can find it quite quickly. Well, you can find any term really. So this method, I like it because we just skip doing the triangle. We basically use Pascal's triangle method without the triangle because we use these things. These things are here called NCR. Now, when do we actually use these things? I mean, yes, we use them in math class. We use them in programming. Binomial coefficients are really helpful for combinatorics, for probabilities. If you're HL, you're going to see these all over the place. I've even seen one used where to distribute IP address. This is a Internet protocol. This is, it's really interesting how they do this. Economics, you can do probabilities based on distributed variables. They actually have to use these binomial coefficients. So there are reasons why you might need them, but if nothing else, you need them for your class. So there you go.